here's what I want you to do for homework. Okay, I want you now to find out the pH when we've gone 9% of the way through the titration. So again, working with the percentages, call 100% the original amount of the weak acid. Berg wants you to find out the pH 9% of the way through. None of this, none of this. Okay, now follow the same format as the last problem. If you do it correctly, you'll find a pH of 7. Okay, now this is the importance of this. Okay, what you have found out is what's called the buffer zone. Okay, now I use the numbers 9% and 91%. Okay, on an exam, it would ask for the pH 10% and 90% through. Well, 9% is almost the same as 10%, and 91% is almost the same as 90%. So we're just trying to get the approximate shape on this also. So you can ignore the numbers 1 to 1, 1 to 10, and 10 to 1 for now. So what you're finding out, what we found out so far, is that halfway through the titration, the pH is equal to the pK sub A. 10% of the way through, it's one number less, and 90% of the way through, it's one number higher than that. Okay, so now that you've seen the trend, you can go ahead and use that on an exam. You don't have to prove it to me. Now, I might ask a question where I say prove it, but if I don't ask for a proof, I want you just to know this. And again, to repeat it again. So halfway through, the pH is equal to the pK sub A, and then it'll be one number less 10% of the way through, and one number greater than that 90% of the way through. And this is called the buffer zone. And on Tuesday's lecture, we're going to have a lecture on buffers. And again, you'll see the buffer zone again. But the buffer zone means the pH doesn't change very much in this region right here. That's why it's called the buffer zone. Okay, so let's see what we've seen so far in the catch method. Okay, so point number 1 is you find the pH halfway through, and it's equal to the pK sub A. And the K sub A was 10 to the minus 8 in a problem, so the pK sub A is 8. And sure enough, that is the pH halfway through. 10% of the way through, I'll call that point number 2, is 1 unit less. So if the pK sub A is 8, the pH there is 7. And 90% of the way through, the pH is 9. Isn't that kind of cool? So we can get those 3 points really, really fast on the titration curve. And our exam, it should take you no more than 10 minutes to do this. Okay, now we're going to grind out the other 3 that take a little time. We're going to get the pH at the beginning, and I'll call that point number 4. Then the pH at the end point, and then pH double the end point. So we're going to work on those 3 points right now. Okay, the pH at the start isn't too bad. It's a typical weak acid equilibrium problem. So the beginning, all you have is the weak acid, and the problem I gave you, it's 10th molar, and no hydrogen or conjugate base yet. The given K sub A was 10 to the minus 8th. Okay, so notice that's the completion step also because of the small size of the K. Now, because we can't have the zeros, you do have a change step taking place, minus x plus x plus x. So here's the equal concentrations, 0.1 minus x, x, and x. Plug these into the mass action expression on the right. Ignore this x right here, okay? And x squared is 10 to the minus 9th. That would be 10 to the minus 8 times 0.1 is 10 to the minus 9th. Okay, I'm going to check my calculator on this. Okay. So x squared is 1e9 minus. Okay, so square root of that is, okay, so I get an answer of 3.16 10 to the minus 5. And minus the log of that is, sure enough, 4.5 is the starting pH. So it takes a little while, but it's just a typical weak acid problem. Now here is the toughie of all of them, and that is the pH at the end point. So for that, you need the titration equation. You've seen this enough times today. I think that should be a problem. Okay, and I didn't show the math on this, but again, how do you get the K sub T? Think alphabetically. It's K sub A over K sub W. So if K sub A is 10 to the minus 8, okay, so that would be 10 to the minus 8 divided by 10 to the minus 14th, which ought to be 10 to the positive 6. And double check, titration reactions always have a positive K. Okay, so let's go through the math of the concentrations. So the problem was 10th molar, 75 milliliters of it, and at the end point, you're going to add 10th molar, 70 milliliters of the conjugate base. So the total volume is 140. After dilution, the concentrations are 0.05 and 0.05. Double check if you really think you're at the endpoint, their concentrations after dilution have to be the same. Okay, now shove it all the way to the right, which means they're both going to be used up completely, but you are going to form some of the conjugate base, 0.05 molar. Okay, so now because of the zeros, you have to back up a little bit in the change steps. So plus x, and minus x. So the equilibrium concentrations are x for molecules of acid, x for the hydroxide, and 0.05 minus x for the A minus. Now, why did I circle in green? Why did I circle the hydroxide there? Because the only way to get the pH at the end point, you've got to solve for hydroxide, get POH and therefore pH. Okay, so let's look at the math of this. So plugging into the mass action expression for the case of T, we have the product of 0.05 minus x for the acetate and x for molecules of acid and hydroxide. Okay, let me check the math on this then. So x squared should be equal to 0.05 divided by 10 to the 6. And so x ought to be the square root of that. So let's see, I'm going to put in my calculator 0.05. We get a pH of 10.35. And again, are you shocked that the pH at the end point is above 7? Not really, because for a weak acid, it should be higher than 7. And why is that again? Look at the titration. You end up with water and the conjugate base. A minus is not a spectator ion, so it's going to grab a hydrogen from water, and therefore what's going to be left are some extra hydroxides. Okay, one more point to get. Let's get the pH double the endpoint. So again, you'll see what's written here is the total titration equation. Okay, now taking dilution into account, let's find out their concentration. So you were given 10th molar of acid, 70 milliliters of it. 10th molar base, Berg wants you to double the endpoint, so you get 140 milliliters. So total volume is 210. So using the dilution factor, the diluted concentrations are 0.033 and 0.066. Okay, completion step, all the acid is neutralized. You have 0. We have some excess base, and we don't care about the other two. Now, what does this solid blue line mean? That's a saving grace here for you, because once you're past the endpoint, you can base the pH on the excess hydroxide. Okay, so POH will be minus log of 0.033. Let me check this on my calculator. So 0.033 is the excess hydroxide. So I'll take minus the log of that. So POH is 1.48 subtracted from 14, and the pH is 12.5. Okay, for homework, I want you to get the same 6 points using the sketch method for 50 milliliters of 10th molar weak acid HX. Notice I've given you the case of A. Notice Berg is not giving you the P case of A, the dirty guy. Now here's a little thing we haven't done yet. You notice so far I've always made the molarity of the acid and the base the same. This time I purposely made the base a different concentration. So a little bit trickier, but great homework problem. Typical Berg exam quiz should be something like this. So make sure you can solve this particular problem for homework. Okay, our next topic is going to be the titration curve for a polyprotic acid. Now, you would think it'd be harder, wouldn't you? In reality, it actually turns out this one is actually slightly easier than the last one we did. Okay, to illustrate how we're going to do this, okay, we're going to start off with 50 milliliter 10th molar. I'm going to use carbonic acid as a polyprotic acid versus 10th molar sodium hydroxide. Now, the secret to success on a polyprotic acid is to break it up into 2 steps. So step number 1 is the molecules of our carbonic acid are going to be attacked by hydroxide. Now, hydroxide is kind of smart. It wants to form nice stable water, but it wants to do it in the easiest possible way. So hydroxide is going to take off the first acid hydrogen of every single carbonic acid molecule first. Okay, you might recall that when you have a polyprotic acid, the first acid comes off the easiest, and it's harder after that. So the hydroxide is just going to react with the first acid hydrogen of every molecule of carbonic acid to form water. Now, after it does that, what are you left with? You're left with hydrogen carbonate. Okay. Now, hydroxide is greedy. It wants to form more water. So here comes step number 2. it's now going to attack every single hydrogen carbonate molecule to form more water, and finally you're left with carbonate. So the point is this takes place in two definite steps. So step one, it removes the easiest acid first, and then it goes after the harder one next. So it does it in two distinct steps. Now, to use these titration equations to get the pH would be really, really hard. But it turns out you can calculate the pH another way, and that is in step number one, besides the titration reaction taking place, you also have the weak acid carbonic acid in equilibrium with hydrogen and its conjugate base. So we're going to use the weak acid system to get the pH. Okay, now given the K sub A1 of carbonic acid is 4.3 times 10 to the minus 7, and the pK sub A of that we minus the log of that. Let's see if that really is true. Let's see if I did that correctly. So 4.3 E7 minus, okay, and take minus the log of that, and sure enough, the pK sub A is 6. I got 6.363. I got 6.37. Okay, I think that's probably right. So 6.37. Okay, so here's the deal. We're going to use the pK sub A1 to find out the pH halfway through the endpoint. Remember that halfway through the endpoint is going to be the pH. Now, to get the rest of the pHs, we're going to use the titration equation, or the weak acid titration for the second part. So in step number 2, we can use the hydrogen carbonate to get the pH. Okay, and again, I've given you K sub A2 for carbonic acid, 6.5 times 10 to the minus, that's 11, by the way. Once you correct your notes, that's a minus 11. And the minus log of that would be K sub A2 would be 10.26. You'd be happy to know that it's still true that molarity of acid times volume acid equal molarity of A times volume of base. Okay, so if you look at the 6.37, how do we get that? That is halfway through the endpoint of the first. Well, first of all, let's back up a little. Notice the 50 milliliters is how much it took for the first endpoint. 100 milliliters, second endpoint. Why are there two endpoints? Because of polyprotic acid. So if you have two acid hydrogens of polyprotic acid, you have two separate endpoints. So what's kind of cool is molarity times volume equals molarity of volume gave us the 50 milliliters to begin with. So once you know the endpoint for the first one, then you know how many milliliters it's going to take for the next one also. Okay, so that's why the 100 milliliters is here. All right, now where did I get the 6.37? That is pK sub A1. So that will tell you the pH halfway through the first endpoint. Okay, how to get the 10.26? That was pK sub A2. So that's kind of cool. Okay, now here's what I want you to do for homework. Okay, I want you to complete as much of this as you can. Okay, so I want you to figure out the pH 10% of the way through the first endpoint, 90% of the way through. Okay, you can probably do those right now. How about 10% of the way through the second endpoint and 90% of the way through the second endpoint? Are they kind of obvious? Okay. Now, you won't be able to get the pH today of the first endpoint or the second endpoint. I'll talk about those on Tuesday. But what I'd like you to try for homework is see if you can figure out the pH to the beginning of this titration curve. And then here is the super challenge. My guess is hardly any of you will really get the right answer. I want you to go to 150 milliliters. I want you to go past the second point at 150 milliliters and figure out the pH right here. Anyway, essentially you've seen a preview of coming attractions for Tuesday's lecture. So all these blank dots you're seeing, we'll discuss those on Tuesday. And I also want to discuss what's so good about this titration curve. What do you know? Well, those that are going into medicine, I'm going to show you how this tells you an awful lot about your body by understanding the titration curve of carbonic acid.